Hey, Math 20-2s. Today we're going to look at normal distribution. The shape of normally distributed data has been discovered that many observations of physical measurements such as length, volume, mass, time, etc. have common characteristics in how their data is distributed. The examples below show histograms developed from data with these common characteristics: weights of infants, time taken to complete all assignments, and heights of students. Draw a frequency polygon by connecting all the midpoints of the top of each bar with a smooth curve. All right, so a nice smooth curve through these. Same thing with this one. And same thing with this one. All right. In each case, the frequency polygon of the data results in a bell-shaped curve. The normal distribution. Data which results in a frequency polygon with a bell-shaped curve is said to be normally distributed. The curve is referred to as a normal distribution curve, or the normal curve, or the bell curve, and it's widely used in making predictions and statistics. Understanding the normal distribution curve. Let's do that by looking at this concrete example. The manufacturer makes 100-watt light bulbs for Glow-Brite Inc. is interested in determining the distribution of the lifetimes of the bulbs. He tested 44 bulbs, calculated the mean life to be about 900 hours, and the standard deviation to be approximately 50 hours. The lifetime in hours of the 44 bulbs tested are shown. So last unit we would have typed all the stuff into list 1, used our calculators to find the mean and standard deviation. We're going to take the approximate values for mean and standard deviation and trust that they're there. All right. Verify the histogram to the data. So all they're saying is, it says here between 750 and 800 hours there is one piece of data. If I go back and look, it looks like there's only one piece of data between 750 and 800 hours. I could do that for all these histogram bars between 800 and 850. It looks like there's supposed to be 6 pieces of data, so 6 in here. So I could check that. If you would like to, you go ahead. We're going to move on. Use the histogram to complete the following table. So number of light bulbs in the interval. Well, less than 800, we said already less than 800 is 1, frequency of 1. Between 8 and 850 is a frequency of 6. Between 850 and 900 light bulbs, that's this bar, there is a frequency of 15. And also in the next one there's a frequency of 15. So between 850 and 900 there were 15 light bulbs, and between 900 and 950 hours 15 light bulbs. Between 950 and 1000, that's this one, and again that's 6 hours. And less than 1000 is right here, and again that is a frequency of 1. So let's complete the percent of bulbs in the interval. So if there's one light bulb out of 44, what is that percentage? So 1 out of 44 gives us a percentage of 0.03%. And then you've got 6 out of 44, which gives us a nice percentage of about 13.64%. And then 15 is done for us, that's 34.09. And we already did 6 again, that's 13.64. And 1 is 0.03%. Perfect. Using a mean of 900 and a standard deviation of 50, write the following numbers in terms of the mean and standard deviation. So if my mean is 900 and I want to get to 950, I have to add 1 standard deviation, or 50. So mean is 900, standard deviation is 50, mean plus standard deviation equals 950. Mean minus 1 standard deviation gives us 850, 900 minus 50. Mean subtract 2 standard deviations will give us 800. And the mean, which is 900, we have to get to 1050. That's 3 sets of 50, or 3 standard deviations. Complete the normal distribution curve based on the results of this example. So our data values, 900 to 950, going up by 50 is 1,000, and 1,050 hours of light bulb. Go down by each standard deviation. Go down by 50, down by 50, down by 50. All right. So this is the mean. It's 0 standard deviations from the mean. 950 is 1 standard deviation from the mean. 1,000 is 2 standard deviations above the mean. 1,050 is 3. This is 1 below, 2 below, and 3 standard deviations below the mean. Data values in terms of mean and standard deviation. Well, 900 is the mean. 950 is the mean plus 1 standard deviation. This is the mean plus 2 standard deviations, and the mean plus 3 standard deviations. Same thing going the other way. The mean minus 1 standard deviation, the mean minus 2 standard deviations, and our mean minus 3 standard deviations. All right. The standard normal distribution curve. So we've talked about the normal curve. Now let's talk about the standard normal curve. All right. So this notation here is not really going to be used in this course, as it says. That terminology and the equation for the standard normal curve are not required for this course. But having this equation is kind of neat. You can type that in your graphing calculator and it'll give you the normal curve if you use these window settings. So this function produces the normal curve. The neat thing to remember is for a standard normal curve, we've got a standard deviation of 1 and a mean of 0. That's a big, big point to remember. All right. So the diagram shows the approximate area under the curve if it's a standard normal distribution. Subdivide into regions, each of a width equal to 1 standard deviation. The percentage of the area under the curve in each region is indicated. All right, so let's complete this table. The mean of the data is 0. There's our mean. The standard deviation of the data is 1. We're going up 1 standard deviation, we're going down 1 standard deviation. The percent of data that is above the mean, if you add all that up, it's going to give you, okay, so the percent of data within 1 standard deviation of the mean. So 1 below and 1 above, we're going to add 34.13 plus 34.13, so 68.26% of the data. Percent of data within 2 standard deviations of the mean. So now we're going to add another 13.59 plus 13.59 onto that. And that would give us 95.44%. And then the numbers, the percent of data within 3 standard deviations of the mean. So now we're going to add another 2.15%. So within 3 standard deviations of the mean will give us 99.74% of the data. Percent of data between 1 and 2 standard deviations above the mean. So between 1 and 2 above the mean, that's this, no, that is this between 1 and 2, 13.59%. All right. And the percent of data that's between 1 and 2 standard deviations below the mean, between 1 and 2 standard deviations below the mean is also 13.59%. So the basic properties of our standard normal distribution curve. The total area under the curve is 1. The normal curve extends indefinitely to the left and to the right. So we're going to go forever left, forever right. We're never ever going to touch the horizontal axis. It'll get closer and closer. The normal curve is symmetric about the mean, meaning half the data is above the mean, 50% this way, and half the data is below the mean, 50% that way. All the data represented by the area, all the data is represented by the area under the curve, and the median, mean, median, and mode all have the same value. All right, they're all right there. Let's try a few examples. A nurse records the number of hours an infant sleeps during a day. He then records the data on a normal distribution curve shown below. The values shown on the horizontal axis differ by 1 standard deviation. So if that is true, we should be able to decide what the mean is. Well, the mean is the middle piece of data. That cuts this thing in half, so the mean is 12 hours. What is a standard deviation? Well, it tells us that each is divided into standard deviations, so from 14 to 12 is 2 hours. So 1 standard deviation is 2 hours. What are the values of A, B, C, and D then? Well, we're going to go down 2 from 10 and down 2 from 8 and up 2 from 14 and up 2 from 16. So A is 6, B is 8, C is 16, D is 18. What percentage of days to the nearest hundredth does the infant sleep between 12 and 14 hours? So what is the area under that curve? So if you go back and look on the last page, that was about 34%. So 34.13%. What percentage of days to the nearest hundredth does the infant sleep between 8 and 16 hours? So between 8 and 16 hours, from here to here, that's going to be within 2 standard deviations of the mean. If you go back and look at the last page, within 2 standard deviations, the mean was 95.44%. And less than 6 hours, we're talking about that area. So below 3 standard deviations, that's going to be about 0.13%. All right. Why is it not possible at this time to determine the percentage of days that the infant sleeps for less than 13 hours? Okay, let's have a look at that real quick. Here's 12, here's 14. We can easily find 13 on the horizontal axis. If I were to draw my line up here, we're looking for less than 13 hours. Well, less than 12 is 50%, so that'd be easy enough to find, but less than 13 doesn't cover that complete segment between 12 and 14, or within 1 standard deviation of the mean. So right now, we do not know how to calculate percentages that show less than complete standard deviations. So to answer part E, we have to look at a concept called z-scores. So the z-scores. It's not possible to, with the given curve in exercise 1, to determine the percentage of days the infant sleeps less than 13 hours because the model of the curve used is limited to integer values of standard deviations. The concept of z-scores can be used to determine this percentage. A z-score for a particular data value is the number of standard deviations the data value is above or below the mean. That's the definition of a z-score. Highlight that, underline that. It is the number of standard deviations the data value is above or below the mean. That's a z-score. So if we look at the last example that has a mean value of 12 and a standard deviation of 2, the value of 18, well, it's 6 hours above 12, but that's 3 sets of 2 or 3 standard deviations above the mean, would therefore have a z-score of 3. A value of 8 is 4 hours below 12, or 2 standard deviations below the mean. That'd have a z-score of -2. Value of 12 is exactly the mean, so that's 0 standard deviations away from the mean, has a z-score of 0. The data value of 13 is 1/2 of a standard deviation above the mean. So we'd say that has a z-score of positive 0.5. So we'll complete the rows below the normal curve. So they've got the data values. In terms of mean and standard deviation, 12 is our mean. 14 is the mean plus 1 standard deviation. 10 is the mean minus 1 standard deviation. 16 is the mean plus 2 standard deviations. 8 is the mean subtract 2 standard deviations. And 18 is our mean add 3 standard deviations. 6 is our mean subtract 3 standard deviations. What does it mean in terms of z-scores? Well, how many standard deviations is 12 away from 12? 0. So 12 has a z-score of 0. How many standard deviations is 14 away from 12? Well, it's 1 above. And 16 is 2 standard deviations above, and 18 is 3 standard deviations above. So they've got z-scores of 1, 2, and 3. 10 is 1 standard deviation below, so it's a -1 z-score. 8 is 2 standard deviations below, that's a -2 z-score, and 6 is 3 standard deviations below the mean, that is a -3 z-score. How can the z-score of a value of 13 be determined? Well, 13 is right here on the horizontal axis, like we said. That is exactly half of a z-score above the mean. So the z-score of 13 should be 1/2, or 0.5. And it's above the mean, so it's positive. All right? So 13 is there. It's got a z-score of 1/2. Here's our z-score formula. You will find this on your formula sheet, and it has all the variables identified for you right here. Z is the z-score, x is the particular data value, mu is the mean, and sigma is the standard deviation. A z-score indicates the number of standard deviations that a data value lies from the mean. A positive z-score means it's above the mean, a negative z-score means it's below the mean. All right? So there is our normal curve listed as a standard normal distribution with z-scores. So a standard normal curve uses z-scores. Complete the following. Approximately 68.3% of the data lie between z-scores of -1 and +1. Right? If you look up here, 68.3 of the data between -1 and +1. Approximately 95.4% of the data lie between a z-score -2 and a z-score +2, and about 99.7% of the data lie between z-scores of -3 and +3. All right. Example 3. The heights in centimeters of 5 starting members of the Wolfhounds basketball team are given. If the mean height is 190 centimeters and the standard deviation is 15 centimeters, calculate the z-score to the nearest hundredth of the tallest player. The one they've done is the shortest player. What's the z-score of 170? So let's follow that for the highest player. The z-score of a player who's 212 centimeters tall would equal x, the data value, 212, minus the mu, the mean, which is 190. Divide that by our standard deviation, which we're told is 15. So if we do that calculation, the z-score of a 212 centimeter tall player should equal 1.46 repeating, so to the nearest hundredth, 1.47. So it's a positive z-score of 1.47 because 212 is greater than the mean, so it's above the mean. Z-scores can be used to compare the data from different normal distributions by converting the distributions to a standard normal distribution. Tony's midterm marks are shown below. Together with the class's mean and standard deviation for every subject, calculate the z-scores to determine which subject Tony performed best in relative to the rest of his class. So let's find the z-score of mathematics. He scored 74, that's the x value. We have to subtract that from the mean. We're told the mean of the math exam was 68. We have to divide that by the standard deviation, which is 12. So his z-score in math would be 6 divided by 12, or 0.5. You guys go ahead and calculate the z-scores for chemistry and physics. Pause it and do that, and then start it again and see how. So the z-score in chemistry would give us 0.43, and the z-score in physics would be 0.18. So answer the question, determine which subject Tony performed best relative to the rest of the class. Well, he's got the highest z-score in math, 0.5. So relative to the rest of the class, Tony performed best in mathematics. Example 5. The average mark on an English exam was 63 and the standard deviation was 12. If the marks were normally distributed and a student's z-score was 1.5, what was the student's actual mark? So you've got your z-score formula. We are looking for the student's actual mark, so we're going to be looking for the x value. We know all the other values in here, so let's substitute in this equation. We know the z-score is 1.5. Z-score 1.5. We don't know his actual mark. That's what we're asked to find. We're told has an average of 63 and a standard deviation of 12. So we should be able to solve this equation for x. So x minus 63 is being divided by 12. I would now multiply both sides of this equation by 12. All right. 12 times 1.5 is 18, and that gives us x minus 63. We should now add 63 to both sides, and 81 would be the student's actual mark. All right, so his actual mark was 81 on that exam. Example 6. The weights of a large shipment of cantaloupes are normally distributed with a mean of 2.3. The weight of a particular cantaloupe is 1.7, which is 1.01 standard deviations below the mean. Determine the standard deviation to the nearest hundredth. So again, using our z-score formula, x minus mean divided by standard deviation. We're asked to find the standard deviation now. So we're told the standard deviation is 1.01 standard deviations below the mean. So my z-score should be negative 1.01. We know the weight of the actual cantaloupe was 1.7. Particular cantaloupe is 1.7. The mean average, or the mean is 2.3. Find the standard deviation. So how do I do this? I'll have to get rid of that denominator standard deviation. So I multiply both sides by the standard deviation. And at the same time, I can do the numerator 1.7 minus 2.3, which is negative 0.6. And now I'm going to divide both sides by negative 1.01 to get my standard deviation. So the standard deviation for this question is 0.59. Example 7. The marks on a math exam at a university were found to have a mean of 52 and a standard deviation of 12. Professor thought the exam was too difficult, so he decided to adjust the original marks by raising the mean to 65 and reducing the standard deviation to 10, but leaving the z-scores unchanged. What would the new mark be for a student who received an original mark of 34%? All right, so let's find out what the z-score of 34% was on the original exam. So the original exam had a mean of 52 and a standard deviation of 12. So a score of 34 should be subtracted from 52 and divided by 12. That's our z-score formula. So let's figure out what the z-score of his original 34% mark was. 34 minus 52 is negative 18, and divide that by 12, and you get negative 1.5. So z-score 34 is negative 1.5. The prof said we're going to leave the z-score unchanged. So my z-score stays as negative 1.5. But I'm going to figure what the new mark would be. So I don't know what x is, but the new average, the new mean is 65, and the new standard deviation is 10. So I should be able to solve for x now, and that'll tell us his new mark. So that's being divided by 10. I want to multiply both sides by 10. So that's negative 15 would equal x minus 65. I'm now going to add 65 to both sides. So his new mark is 50. So the student would be pretty happy. Would have got 34%. Change his mark to 50. He's still ranked the same in the class because his z-score hasn't changed. All right. Great. You've got this assignment. Away you go.